So hi everyone. To start our discussion of metal-ligand bonding, that's the topic in chapter 10. We're going to first introduce some of the concepts of the thermodynamics of metal-ligand bonding. And of course, it always falls back to sort of the fundamental relationships in thermodynamics. So of course, delta G is equal to delta H minus T delta S. And then that free energy change that's corresponding to the given reaction is related to the reaction's equilibrium constant by the expression delta G is minus RT ln K. So that's going to be the basis for everything we sort of discuss in this approach. So formation constants are also known as stability constants, and they're effectively just equilibrium constants, but they describe the formation of coordination compounds from typically the agua or agua starting materials, because most of these reactions will take place in aqueous solution. But the equilibrium constants are really giving you, again, a relative idea of how much the free energy change associated with the reaction in making new metal-ligand bonds. So the typical approach is if the K value for the equilibrium constant is much greater than 1, the equilibrium is favoring the product formation. And then that's really implying that the newly formed compounds are more stable with respect to the starting materials. So a typical reaction is represented here. So here we have the hexaagua complex of copper 2+, and that's reacting with 4 equivalents of NH3. So making we're going to make the amine complex. And then as a result of that reaction, you do form the tetramine bisagua complex. And in the end, that reaction has an equilibrium constant, and that equilibrium constant is actually 1 times 10 to the 13th. So that reaction is incredibly favored for product formation, effectively by 13 orders of magnitude. And it's telling you that producing copper NH3 bond seems to be much more favorable than having the copper to water bonds. So the whole goal of this chapter is going to be how can we correlate these thermodynamic parameters to electronic structure. But let's go into some of the more fine details. Oh, another thing I should mention is because these equilibrium constants can be very large, sometimes you'll actually see them reported as log K. So in this case, log of K would be 13. So it just makes the numbers more manageable. So we'll see that occasionally in problems you encounter. So the first thing is we can look at that same exact reaction and written as the overall process. This is the net result. So I'm just copying effectively what was on the previous page. But what you can do to describe this reaction in a little more detail is to worry about how you stepwise form the final product. So what you're basically doing is you can add 1 ligand at a time. And when you do that in each step, those are called stepwise formation constants. And the stepwise formation constants sometimes are given equilibrium values. So you'll see it written as K1, for example, for the first reaction. But you'll also see them written in terms of beta as well. And beta sub n and K sub n are completely interchangeable in these exercises. You're going to see it both ways because there was sort of the old nomenclature way of doing this was with beta. The newer way of doing it is with K values. So whatever makes you happier, I give it to you both ways here. So really what you're doing when you're adding 1 ligand at a time is shown here. So if you start with again, the hexagonal complex of copper 2 plus, you're adding one equivalent of the amine to then give you effectively the first compound, where you basically installed the first ligand L in one shot. And then that has an equilibrium constant that's affiliated with that reaction. And of course, it's just written there, and water drops out of the expression because obviously you're doing the reaction in aqueous solution, and water is a pure liquid. So that concentration is invariant and will not change. So keep going. You then add the second ligand. So now this is, basically this is now putting the second ligand in place. And then following through, you can kind of continue the same process. So this is obviously now K2 or beta 2. And then you do the third ligand. So this is for the third ligand step to be put in place. And again, you get the K3 values. And then finally, for the fourth reaction, that winds up giving us the actual product that is in the overall reaction up top. And because that is the way it's written, what you're basically going to realize is, and this is just going back to general chemistry concepts, is that the products of every one of these steps will give you the overall reaction that's actually written up top there. So the other thing about this, which is very normal, is the first ligand typically goes on much easier with respect to the second ligand. And that means the equilibrium constant for K1 is greater than K2, but then putting on the second one is actually is a greater probability than putting it on in the third reaction. And then finally, the fourth reaction is typically the lowest in terms of equilibrium constant value. So the beta values follow suit exactly the same process. But what you should recognize is when you don't see these trends, what's going to typically occur is there's going to be typically some type of massive change in geometry or some type of massive change in the electronic structure in some way that actually is perturbing the values of these numbers. And that's why we're going to, want to look at that as the starting point, because we are going to use this later to justify how electronic structures change in the formation of transition metal complexes as a function of ligand and as a function of sort of stoichiometry. So we're going to see a lot of this later. And then finally, as I told you, the overall reaction that's up top here is simply the product of all the individual steps.